In this task, we're asked to calculate the maximum density for the distributed loading Q when the beam is made out of aluminium and the cross section is as shown in the picture, and the yield strength of that aluminium is 220 megapascals. Um, the formula for bending stress, we know it goes like this: the sigma equals to internal bending force divided by section modulus. In this task, we already know what is sigma. It is given. It is 220 megapascals. Bending moment, we have to use statics to solve this one. And finally, the section modulus, Wy, we need to solve using the subtraction method. So the first thing in this task is that we start by doing the free body diagram and doing the equilibrium equations and solving all the forces, and then solving what is the maximum value for the bending load in the structure. Where is it? Where does it locate? So let's first start by drawing the free body diagram. On the left hand side we have FAY, FAX, and on the right hand side we have FBY. And now in statics, you remember that you can you can combine the distributed loading as an equilibrium or as an local point load. You can mark it with this kind of symbol, and this is value Q times 800 millimeters. In the task, the length of this distributed loading is 800 millimeters, and the density is Q, so the value for this distributed loading as a point load is Q times 800 millimeters. Let's do the equilibrium equations then. So sum of all forces horizontal direction are 0. Horizontal forces to positive direction we have FAX, but that is the only load in horizontal direction, so this one has to be equal to 0. Then sum of all forces in vertical direction, they must be also 0. In vertical direction we have FAY to positive direction. Then we have Q times 800 to negative direction, and then we finally have also FBY to positive direction, like so. And this one has to be 0. And finally we have sum of all the moments must be 0. In this task I will do this around point A. So point A, it is this left hand side here. This is point A here. So it means that our external distributed loading Q is rotating our structure to the negative direction, so minus Q times 800 multiplied by the distance from here to the middle, that was 700 millimeters, halfway to the beam. The length of the beam was 1400, plus Our FBY is rotating to positive direction, counterclockwise, which is the positive direction. And we have here FBY multiplied by 1400 millimeters, and this as well has to be 0. So these are equation 3, equation 2, and equation 1. How can we solve this? Well, from equation 3 we can solve what is FBY. FBY has to be Q times 800 millimeters times 700 millimeters divided by 1400. So FBY is Q times 400. Well, from the equation 2 we can now solve that FAY equals to Q times 400. So now we have solved all the loads, all the reaction forces here. So now we can go forward to doing the shear force diagram and bending moment diagram. In this example, because we have distributed loading here, we are going to need to do also the shear force diagram, because in the shear force diagram you remember from statics that when the value for shear force goes to 0 or crosses the y-axis, it means that that is the location where the bending stress gets its bending load gets its highest value, or at least local minimum or local maximum. Okay, so let's draw the free body diagram here, but this time we know the forces here or the support reactions, so let's draw them all here like this one here. Now you remember that at this stage we can no longer combine the distributed loading as a one load. Instead we must have it drawn separately here. So we have distributed loading here. This is our Q, like that one. So this is Q. In here we have force Q times 400. And here we also have force Q times 400, like that. The length from here to here, this one is 300. Length from here to here, this one is 800. And the last one here is also 300. So let's start by drawing the shear force diagram. So let's draw the shear force diagram here. Like that. So here we have the diagram. So at the beginning here, when we start from here, we have shear force pointing, we have a support force on the left hand side pointing upwards, which means that the internal shear force inside the material is pointing downwards. And we remember our sign convention, this means that it is positive value. So it goes here and it goes to positive Q times 400. It will remain on that level until we reach this point until we reach this point where we have our start of the distributed loading here. So from this point forward, the distributed loading is going to be reducing our internal shear force because the force is pointing to other direction. When we reach the halfway, this point here, where we have had 400 millimeters of the Q, it means that the Q400, which we had here, will be at 0 here. Our shear force will be 0 when we are halfway through. And we will continue on this linear slope all the way to this here, where we reach negative Q400. And then we will remain on that level until we reach the end of the structure, where we finally have once again Q400 pointing upwards, which means that our internal shear force will go to 0 like it's supposed to go. So here we have positive value, here we have negative value. Like that. Well, the next step. Next we are going to need to solve what is the internal bending moment in this structure. Let's draw here a diagram. Let's draw here a diagram. Let's highlight the location where the forces are. Like so. So when we start at the beginning, we don't have any bending moment, so we are at 0. We start from 0. The Q400 will start to increase our bending moment, and when we go from here to the beginning of distributed loading, we're gonna go for distance 300. So we're gonna go we're gonna go here, location number 1. We can calculate in the location number 1 our bending moment, internal bending moment, will be Q times 400, which is the external support force which we have here, multiplied by the distance of 300 millimeters, which means that the value will be Q times power to 2, like that one. So we are gonna start from 0 and we are gonna go linearly to value Q times 120 power to 3. Okay, so that's our internal bending moment there. All right. Well, then you remember that that distributed loading causes like parabolic distribution in bending moment, and when we go from the point 1 to halfway of this distributed loading, that is the point where we are going to have local minimum or local maximum of bending moment. So next thing is that we are going to be solving what is the bending moment at that location. The bending moment at that location will be Q times 400. So that is the support on the left end here, and the distance from there to the middle of the beam will be 700. let's leave those millimeters away from here. So 400 times 700, and then the distributed loading is rotating it to opposite direction, so we have to reduce that one. So the distributed loading here, when we go to halfway here, it is Q times 400 as well. And the length of the length that is rotating this one is 200. And the value here will be Q times 200 times 10 to power 3 millimeters power to 2, like that one. So parabolic curve, and that's where we will land. That's location 2. And then we can solve it for location 3, but since the scenario is symmetric, we know that at location 3 the load will be the same as it was in location 1. And then finally, at the end of this beam, we are gonna be back at 0, which means that we will go linearly to 0. And from here we can see that the maximum value for our stress will be, for our internal bending moment, will be Q times 200 times 10 to power 3 millimeters power to 2. So that is our maximum value for the bending stress, for the internal bending moment. Now we finally can go forward to calculating what is the stress in the structure, and we have to do the calculation of the second moment of inertia for the profile which we have here. So we have a rectangular profile that has a hole in the middle of it, like so. So this will be our additional y-axis. The actual y-axis is gonna be located somewhere in here. The diameter of this round part is 30 millimeters. The width is 40, and the height is 50. So those are the dimensions of the rectangle here. First thing which we have to do is to find out the Z0. And that we do by calculating like so. So 50 millimeters times 40 millimeters, it's the area of the rectangle, multiplied by the distance from the neutral axis of the rectangle to the additional axis, which will be 25. And then we have to use the subtraction method, so we're going to reduce from this one the area of the hole, which is pi times 15 power to 2. Diameter was 30, so radius is 15. Multiplied by the distance from the neutral axis of the circle to the edge of the profile. It is, in this task, it is 20 millimeters. This was already given in the assignment in here. It is given in here. And then we have to divide this entire thing with the cross-section area of the entire profile, which is 50 times 40 minus pi times 15 power to 2. And what we get from here is that the Z is 27.7 millimeters from the top. This profile is symmetric along this axis, and we are only calculating around the y-axis, so we don't need to solve what is the location of y0 in this profile. So that is enough for now. Next, what we can do, or what we need to do, is that we need to solve what is the second moment of inertia of this profile around the y-axis, Iy. And that is second moment of inertia of the entire profile of the rectangle, which is 40 millimeters by 50 millimeters power to 3 divided by 12 multiplied by the Steiner and add here the Steiner term, which is plus area 40 times 50 times the distance from the neutral axis of the rectangle to the neutral axis of entire profile, which is 2.3 power to 2. And then we have to reduce from here the second moment of inertia of that hole in here, which is for round objects, it's pi times diameter power to 4 divided by 64. And we have to add here also the Steiner's term, which is pi radius power to 2 times the distance from the neutral axis of this one to the center of the neutral axis of the entire profile, which is 7.3 power to 2, like so. And the value will be 349.6 10 to power 3 millimeters power to 4, like so. From this one, we can very simply solve what is the section modulus. Well, section modulus is the Iy divided by Z max, which will be in this case 349.6 10 to power 3 divided by the Z max, which is in this case it is 27.7. And this will give us 12.6 10 to power 3 millimeters power to 3. Alright, so now we have solved the section modulus for this cross section. We now know what is the bending moment, internal bending moment, maximum value. We know what is the section modulus. We know what is the maximum allowed stress that this material can withstand. So now we can solve what is the Q that this structure can withstand. So how we calculate that one? Let's bring in here the equation. Sigma is internal bending moment divided by the section modulus here, and from this one we can make the maximum stress for our material was 220, and that equals to the bending moment, which we calculated was Q times 200 times 10 to power 3 millimeters power to 2 divided by the section modulus, which is 12.6 10 to power 3 millimeters power to 3. And when we solve from this equation the Q, we get Q is 220 times 12.6 10 to power 3 divided by 200 times 10 to power 3 And what we get is 13.9 newtons per millimeter. So that was the answer for our task. The maximum distribution, the maximum density for the distributed loading is 13.9 newtons per millimeter.